In this video, you will simulate a synthesis gas production facility. This will introduce you to the reaction modeling capabilities of aspen hysys. You will define chemical reactions and reactor unit operation models in aspen hysys. You will also work with various logical operations to automate certain specifications and meet targets in your model. This video includes the following tasks. Task 1. Isolate the natural gas feed. Task 2. Set up reactions and reaction cells. Task 3. Build the synthetic gas process. Task 1. Isolate the natural gas feed. One of the products from the turbo expander natural gas liquid fractionation plant is a high-pressure gas product mainly consisting of methane. It has been decided to split off a fraction of this gas product for sale to a neighboring plant with a synthesis gas production facility. In the hysys simulation, you need to isolate the desired amount of natural gas flow for transmission to the syngas plant. The natural gas also needs to be brought to the proper conditions for the syngas process. Open the attached file with this video. Break the connection between stream 15 and export gas compressor. Add a T. Name the outlet stream. On the worksheet tab, set the molar flow of the two syngas to 19 kg mole per hour. Connect the export gas stream to the export gas compressor. The synthesis gas process will be modeled with your flow sheet, but to avoid having a main flow sheet window with excessive amounts of operations and streams, we will make use of the subflow sheet modeling capability of aspen hysys and place the syngas process inside its own subflow sheet. Add a blank subflow sheet from the object palette. Start with a blank flow sheet. Name the subflow sheet syngas plant. List to syngas as an external stream in the inlet connections list. Click subflow sheet environment. The two syngas material stream you see in the subflow sheet is a mixture of light and medium hydrocarbons, carbon dioxide, nitrogen, and a small amount of water. This stream needs to be compressed and heated to certain conditions before it can enter the synthetic gas reactor train. It's also important to consider the components present in the stream and how they will react in the synthesis gas process. The syngas stream is primarily composed of methane, but there is also a small amount of ethane, propane, butanes, etc. As part of the synthesis gas process, combustion of methane is a reaction of interest. If methane is present and combusted, it can be reasoned that any other hydrocarbons would be combusted as well. To simplify the reaction definitions, you will remove any hydrocarbons heavier than propane prior to feeding the gas into the first reactor, thus ignoring the combustion of any heavier hydrocarbons. Add a compressor. Define the outlet and energy streams. Set the outlet stream pressure to 3,500 kilopascal. The high pressure gas stream needs to feed into the reaction section at 370 degrees centigrade. Add a heater. Define energy and outlet streams. Set delta B to 0 kilopascal. Set the outlet stream temperature to 370 degrees centigrade. The last step before setting up the reactions and reactors is to remove all hydrocarbons heavier than propane from the reactor train feed. Add component splitter. Define the overhead and bottoms outlet and energy streams. To the parameters form, set the natural gas and the heavy hydrocarbon temperature to 370. Select equalize all streams pressures. Move to the splits form. Enter a split of 1 for nitrogen, carbon dioxide, methane, ethane, propane, and water. Enter a split of 0 for all other species. Please note that these values are defined for the natural gas stream. This concludes the first task in our video. Task 2. Set up reactions and reaction sets. The definition of any chemical reactions to be considered within a hysys flow sheet must be made in the properties environment. All tools and features needed for specifying various classes of reactions are available there. Once the reactions have been defined, specified, and properly assigned to the active fluid package, they can be used in the simulation environment. One more thing to consider: make sure any components needed for the reactions are specified in your component list. Now navigate to the properties environment. Select component list. Add carbon monoxide and hydrogen and oxygen to the component list. Select the reactions folder. Click Add. Rename the added reaction set to combustor reaction set. Reactions. Click Add Reaction. Keep the default reactant source and reaction type. Add 5 more reactions. Now expand the combustor reaction set. Select the first reaction. In the stoichiometry info section, list out methane, water, and carbon monoxide and hydrogen. Set the stoichiometric coefficient of methane and water to -1. And the stoichiometric coefficient for CO2 to 1. And for hydrogen to 3. Make sure that methane is shown as the base component. Enter a percentage conversion of 35% in the C0 field. Continue by defining the other 4 conversion reactions in the combustor reaction set using the following characteristics. After defining the reaction, return to the combustor reaction set. Click the Add to Fluid Package button. Click Add. Now add another reaction set. Name this reaction set as Shift Reaction Set. Click Add Reaction and choose Equilibrium as the reaction type. Navigate to the added reaction. Navigate to the Library tab. Highlight the first reaction and click Add Library Reaction. Navigate back to the shift reaction set. Select Add to Fluid Package. Click Add. Add one final reaction set. Name it Reformer Reaction Set. Click the pull-down arrow on the Add Reaction button. Select Existing Reaction. Select Reaction 1 and 2. Attach to the Basis 1 fluid package. This concludes the second task in our video. Task 3. Build the synthesis gas process. There are 6 different reactor unit operation types in aspen hysys. By using combinations of these 6 operations, virtually any reactor can be modeled given sufficient information. The 6 reactor types available are conversion, yield shift, equilibrium, Gibbs, continuously stirred tank reactor, CSTR, and a plug flow reactor, PFR. Navigate back to the simulation environment. Create 3 new material streams with the following inputs. The first reactor in the synthesis gas plant is the reformer. This reactor will be modeled as a conversion reactor, and it will utilize the reformer reaction set. Attach natural gas and reformer steam as inlet streams. Name the vapor outlet combustor feed and the energy stream as reformer Q. Even though there will be no liquid flow from this reactor, you still must create a liquid phase product stream for flow sheet connectivity purpose. Name the liquid product stream as reformer LP. Move to the reaction details form. Set the reaction set to the reformer reaction set. Select conversion percent radio button. Set C0 for reaction 2 to 30% and for reaction 1 to 40%. Navigate to the worksheet tab and enter a temperature of 930 degrees centigrade for the outlet stream combustor feed on the worksheet tab. At this stage, the first reactor will not solve yet. The pressure is unknown in the reformer steam stream. As you build the flow sheet, you will use a logical operation set to define this pressure, but you will add the next reactor in the sequence first. second reactor in a synthesis gas plant is the combustor. The combustor will be modeled as a conversion reactor and an equilibrium reactor in series. This is because conversion reactions and equilibrium reactions cannot occur in reactors of the opposite type. Add another conversion reactor to your flow sheet. Add air and combustor steam and combustor feed to the outlets. Name the vapor outlet mid-combust. And the liquid outlet combustor LP. Set the reaction set to combustor reaction set. Keep all other parameters to default. Remember that you didn't enter any pressure data for the air or steam streams. Add 3 set operation to set the pressure of the reformer steam and the combustor steam and the air to the pressure of the natural gas stream. As mentioned before, the combustor is to be modeled as a conversion reactor followed by an equilibrium reactor. So you must still add the equilibrium side of the combustion. The shift reactors will also be modeled as 2 equilibrium reactors. Therefore, a total 3 equilibrium reactors must be added to complete the flow sheet. Set the temperature of stream 2 to 450 degrees centigrade and the temperature of stream 6 to 400. Set the reaction set to shift reaction set for the 3 reactors and add an energy stream for the last 2 reactors. This concludes the last task in our video. Thank you for watching.